you know the what your conditions are there at the boundaries. Now you want to solve that. So in that case, again, you have two type of equations. The first one could be your ordinary differential equation. Again, it could be a first order equations, and it could be a second order equation. Okay.
Yes, sir.
But you know the actually your boundaries. So the boundary value problem means you know the means either functions or derivative, or maybe the both, depending on type of equations. You know the means values at the boundary. You are supposed to solve actually that how to get the solution in between of those points actually. So if I in that case, the derivatives can be calculated either by your using your Taylor series expansion. So if you use your Taylor series expansion actually, so you can calculate your first derivative and second derivatives, and there are some difference tables also there. The means the you did your finite the difference techniques, the right. So in that you have calculated the means difference of that. So based on that also you can calculate also your means that finite difference tables can also be used to calculate the derivative actually. So in that case, if you want to use your finite difference and central difference formula, or your forward difference formula, or your backward difference formula, so all of them can be used to calculate your actually your derivative. Suppose and people most of the time is being preferred your center difference formula. So most of the time people prefer that one. So let's see that how to use that thing actually is that the central difference formula and all this has to calculate, I mean, the solve your boundary value mean the problem. So if I show you this one, can you, actually you cannot see. Let me see. Can you see the screen?
Yes,
Yes,
sir.
sir.
Yes.
Yes, sir.
Okay, so what we have here, this we will start. Let's say, where should I start? Yeah. Let me give the label of this one. This one. Okay, we can go from here actually, not for this one. So probably we can start maybe cylinder. No, let's start from metal ball actually. Differential equations, spherical. This one actually. So what we have, are you also seeing the multiple files? So, so let's say we are taking a typical example of heat transfer in this. Let's say this is actually you can say, can you see this picture?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
So this, let's say, is practically a one-dimensional heat transfer. You have a rod, or you can say a cylinder or rod, anything, but you are considering transfer is, let's say, one-dimensional only. So what you have here, that in this case, at this boundary at x equal to 0, or let's say you know here what is your temperature. Let's say we are the solving it for temperature case. So in that case, let's say here we know the temperature here. Either we know the temperature value or let's say that the derivative. Let's say here conditions are known to us. So condition could be in case of heat transfer, could be your condition are actually fixed. Means either fixed means either you would have let's say temperature either mean the known to you here, or let's say the derivative of the temperature could be known to you. So either you know the temperature boundary conditions or flux boundary condition, or you know the how much flux is coming from here. Okay. So these are the two typical boundary conditions in the heat transfer, either temperature or flux. So same thing here. So the suppose you know the conditions here and you want to solve them here. So let's say typical is one-dimensional heat transfer in a metal bar. Now what you have here, these are this you can say this is your problem statement for that. Suppose we want to solve it first for temperature boundary conditions. So for temperature boundary conditions, let's see here at T equal to T. Let me change this setting first. Let me. So let's say we were the here for that, but we have here the problem statement is, let's say at T at x equal to 0 is given to you T naught, and temperature at x equal to L is given at TL. Okay. And XL we are just mean the actually the mean the putting it here. XL is the end coordinate of the bar and X naught is the initial coordinate. So we have to choose a coordinate system here. And we want to calculate is values of this function, let's say temperature, at n number of difference points in between of this initial and final values. And this is what is your figure is actually here. So from here to here, you want to calculate n difference point, and you want to find the what should be your value of temperature at all these difference points here in between of that only. Okay. So if you will see that, let's say your general heat transfer here. So if you read a general heat transfer here in this particular case, so this you can write a heat transfer equations in your rectangular coordinate based on your Fick's law actually. So what you have here, this is you can say your fluxes in your actually x direction. This is again your fluxes in y direction here. This is again your fluxes in z directions. And if you add them up, and this is the E dot the generation, means how much energy or heat is being generated within the material. So this is the generation per unit volume actually, equal to rho Cp del T upon the del T. So this term is practically rate of accumulation of energy within the material here. So I don't hope I need to do the derivation of this. This means equation. This is very well-known equation. So if you want the derivation, you can search it, or I can share you that particular part. Our part is we want to solve it actually. Okay.
Yes, sir.
Yes, sir.
So let's say we want to solve it, solve it only in x directions, or let's say along the length of the bar actually. So in that case, either of two terms should be cancelled. That choice is yours. So in that figure, we are considering, let's say x is along the direction of along the length. So we are just cancelling that that y term and dz term there. At the same time, for this case, in this case, we have considered that we are not considering any sort of generation of heat. Means we have not inserted any, let's say, heater here or some chemical fuel here from where heat is getting the generated. So there no heat the generation within this entire material. Outside of that, you can the supplied heat and all this, that's not being treated the E dot generation within the material. So because the within the material you are not generating any sort of heat by any means, either by the the electrical heating or by chemical the reaction, you are not doing that. So for that particular region here, this E dot the generation is also being considered zero. No heat generation within the material here. Now, for the time being at primary stage, we are considering that let's say let's solve it for a steady state operation. So if you want to solve it for a steady state operation there, so this del t upon del t, because the nothing would be a function of time. So this term would get cancelled. Practically, there would not be any accumulation term. So this term will get cancelled. So if you will say that no heat the generation and under the the steady state condition, this equation can be rewritten into this particular form, and again you are cancelling that no heat transfer in y direction, no heat transfer in z direction. So you will end up with this equation here, that del upon del x equal to del upon del x k del t upon del x equal to 0. Now, in this case, because you are considering that temperature is only the function of x only, so your partial the derivative would be converted to total the derivative. So this del sign would become now the full that the derivative. Second part, you are also considering that given temperature range in the such that you are considering that thermal conductivity is not varying too much, or in this particular the range of given temperature, the range for which you want to solve this equation actually, so this particular problem. So let's say the k is independent of the temperature. So in that case, k would not be a function of temperature, and again you are considering that this is the isentropic the material. So for that particular purpose, you are just saying that the k is also not a function of x. It is not the space function actually. For isentropic material, the property of the material doesn't change with respect to coordinate system. So in that case, k would also come out from the here. So finally, you will write here d square t upon dx square equal to 0. So this equation need to be solved in case of steady state heat transfer, one dimensional heat transfer in any of the things actually. Maybe you have the cylinder or anything. Currently, you are talking about the rod. So this is on one dimensional heat transfer in the rod under the steady state. So you have double the derivative here. Practically, it needs a two boundary conditions. Correct? Hello.
Yes, sir.
Yes,
Yes,
sir.
Now,
sir.
okay, let's see what boundary conditions we have here. So here you want to solve it here. So this looks for you easy that you can the integrate it twice and you can solve it, right? So that's it, the analytical solution. Correct? Because if you want to
Yes,
solve
sir.
it means analytically this one, so you will just integrate one that dt upon dx equal to your first thing is your what would come your first means integration dt upon dx equal to 0 plus C1,
Constant.
right?
Yes, sir. Yes, sir.
Then you want to integrate one more time, so you will get t equal to C1x plus C1x plus C2,
C2.
right? So you know
Yes, sir.
the two boundary condition, plug them out, you can solve it means analytically here. So for this, you can say for this the analytical solution is the easy, but it's not possible at all times. So let's say for this we want to solve it by the numerical techniques. So there are several the numerical techniques just to calculate the double the derivative. So if you take your Taylor series expansion actually, so if you say that Taylor series expansion, can you recall what Taylor series expansion is? So you have let's say you have this fx. Can you recall your Taylor series expansion?
Yes, sir.
What is that?
Sir, y of x plus h is equal to y of x plus h y dash x by 1 factorial plus h
Right.
y double dash x by 2 factorial and so on.
And it will continue of the something like that, correct?
Yes, sir.
Yes, sir.
Now, based on that, if you want to calculate, let's say you want to cancel other means higher order term, keeping only first difference term there. So you have one side is fx plus h equal to your fx plus h f dash x, correct?
Yes, sir.
So f dash x is the nothing but your first derivative, right?
Yes, sir.
Yes, sir.
Correct. So your first derivative would become your practically your fx plus h minus your fx divided by h, right?
Yes, sir.
This is your first derivative.
Yes,
Now,
sir.
can we calculate the same way the second the derivative? Can it be possible? Let's say we want to calculate our the second the derivative also. In between of this actually at this particular place, let's say we want to have here. So
So
there
yes, sir. So for
uh,
second derivative, we would need f of x plus h as well as f of x minus h, and then
just
after
wait.
applying optimization.
Currently we got here, let's say we can write this particular format here. So you got just now your f dash f के जगह अब for time being, let's say you can take the t actually dt upon this dx equal to, you are just getting, what are you mean the getting just now? You are getting the t, but you are getting x plus h, right?
Yes, sir.
Yes, sir.
Minus tx divided by your h, right?
H. Yes, sir.
Yes, sir.
So this is your first derivative, fine,
Yes, sir.
correct? Suppose we want the now this could be your actually function only. This could be means any function, right? Yes or no? For time being.
Yes, sir.
Yes, sir. Yes, sir.
Now we want to calculate the derivative of this again. So let's say we want to calculate a derivative of this f again. What will you do? You will again calculate your f dash at x plus h, right? minus fx. Hello?
Yes, sir.
Yes, sir. Yes, sir.
1 minute. And divided by again your h, right?
Yes, sir.
Yes, sir.
Correct or not? Now, let's say what is your function. So this total thing, you want to calculate 1 at x plus h. So let's say you have the substituted this whole thing here, which you are calculating at x plus h. And now this one again, you are calculating at fx. Correct? Hello?
Yes, sir. The values will change according to tx. Sir, like t of x minus t of x minus h.
Yeah, so what should I the write here actually? Or let's say come back again from there you have f x plus h equal to your fx plus h. You have here f dash x, right? H f dash x. Can we write the
Yes, sir.
second derivative also here? What is that? Can anyone tell?
H f
H
h
square upon
f
2 factorial.
Okay, so let's write that one. So h square upon factorial 2, and that you have here f
F
double
f
dash
double
x,
double
dash
dash.
right?
x.
So let's say you got the first derivative from here. So first derivative you got this one. Now let's say you want to calculate the second derivative using this equation, right? Can you
Yes, sir.
calculate from the there? What would be your the equation for f double dash x?
F of x plus h minus
So
f
you
of
have
x.
practically this fx x plus h. You will minus this one also, and you are again taking this also, right?
Yes, sir.
Correct or not? With minus sign. Now this you have already fixed up at the something at the at this particular side here. So how would I calculate this? Hello? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. So what will you do here further? Just keep on telling me this one. So here you want this one. इसके आगे का बोलिए. What will I write after this? यहाँ तक तो ठीक है ना? What would I
Sir,
write
we
after
can.
this?
Yes, sir.
So can we replace f of x plus h minus f of x by h into
Yes, yes. That's
f
what.
dash of x?
Yes, yes. That's what you do here. So if you will do that here, so f dash x you have from here. This was practically just nothing but your f dash x, right? So that if you
Yes,
will
sir.
substitute from here, what will you get? So at this place also you can write again your same thing. And this h will get cancelled, right? Because you have h
Yes, sir.
at both the places.
Yes, sir.
Am I doing correct or there's something wrong is going on? Now, what should I write here? Is it fine? Hello?
Yes, sir.
Yes, sir.
What will come after this?
सर ब्रैकेट ओपन करने के बाद तो कैंसिल हो जा रहा है सर.
Yes.
Yes, sir.
So, what to do?
We need some other operation.
What?
Sir, we can write the Taylor series expansion for f of x minus h, and then by adding them, we can find out the value of f double dash x.
No copy. Huh?
So we can write the Taylor series expansion for f of x minus h as well, and then up
Right,
to two
right.
derivatives.
Now you
And then
came to
after,
the, yes, yes, yes. You are the right now. Now you got next one. You write for x minus h. Okay. So you can write the same thing, and only thing this term would be minus, right?
yes,
Yes,
sir.
sir.
We are not means the considering other means the higher order term. So let's focus for one by one here. Let's say for time being ये भी आपने हटा दिया. You are just considering only first two term only, first term only. Let's say you want to calculate your first derivative only. Okay, just first derivative only this. If you will subtract first from the second, what will you get? Subtract, let's say this I say first one. Sorry, this I am saying equation 1, and this I am checking, let's say equation number 2. Fine. Now I just want to do equation number 1 minus 2. Can I do that?
Sir,
Yes, sir.
f x plus
F.
h minus f
Yes.
x minus h upon 2h minus
Minus f
x minus
x
h
minus h
upon 2h
upon 2h
is equal to f derivative x.
upon 2h is actually your f dash h, right?
Yes, sir.
So
Yes, sir.
this is the nothing but it's called your central difference formula of first derivative. Okay. Previous one you are just calculating here. This was the first derivative based on your forward difference. Fine.
Yes, sir.
If you will
Yes,
just
sir.
calculate from here, this one, just calculate from here your f dash s. That is your first derivative based on your backward difference. Okay.
Yes, sir.
Now, if you are taking off these two, then this is called your first derivative based on your central, mean the difference one. And most of the time, people prefer this one only because this is much more accurate as compared to the forward and backward. Based on people's practice. Okay. So if I write this term in terms of I and j, so what will I write here? It will become, let's say, your I plus 1, right? And it will become thus I minus 1, right?
Yes, sir.
Correct. So if I write in terms of I and j, because I have to make a program for that. So for me, it looks better if I can write in terms of I and j, right? Correct.
Yes, sir.
Yes, sir.
Fine. Now, once I will put I equal to 1, what will I get here? F naught equal to F naught, right? Correct or not?
Yes, sir. Yes, sir.
That would be my boundary. So I already know the function value at my means the boundary, right? When I put I equal to n, I will get here that I n plus 1, that is again the boundary one, the last point.
Yes,
Okay.
sir.
So so those boundary would always would be the taken care by the this, and rest of the thing would be solved. Now let's say, can we write the second difference formula? Mean the central difference formula for the second the derivative. So can I add this one in the in इनको add कर देंगे?
Yes, sir.
So let's see what will come after adding. Add this equation. So let's say if you want to rewrite them. So just you can write here equation number. Let's say this is 3, and this one is equation number 4. Just add equation number 3 to your 4. What will you get? So you can write here maybe this one, maybe this one.
Sir, f double derivative is equal to f x
Equal
plus h.
to, you will get here I think 2 fx plus this would become how much is there? Half would become full, right?
H square, sir.
Yeah.
Sir, h square f double derivative x.
So this would become x square. Now from here I can get my expression for your second derivative. The second derivative would be, let's say I can write this one. In between of that I can write this particular thing here. Minus of this, right? And divided by my h square. Correct?
Yes, sir.
This
Yes,
is
sir.
your the expression for your derivative, or second the derivative, central the difference formula for your second the derivative. Fine. So if you want to write in terms of I and j again, so what will I write here? You will have here I plus 1. Here this would be just I, and this would be your I minus 1.
Yes, sir.
What is h? Difference between two i's, right? How far they are, right? That is your h.
Yes, sir.
Correct?
Yes, sir.
Now, can we go back to our, let's insert, let's say this one. So this is what you got from here. Is it visible? ज़्यादा छोटा है. जो wrong था उसको हटा दीजिए. No, it's fine. So based on that, I did the same thing here. So you are solving your equation. What was your equation here? Your equation was this: del square t upon del x square, right?
Yes, sir.
Now for
Yes,
this,
sir. Yes, sir.
you can use the central difference formulation just to calculate your second derivative. And if you will do that, so practically you will get this. So I did here, this is what you have your the expression for your the second the derivative, which I wrote just now to you. Correct?
Yes, sir.
Right? Now this h is the delta x is the nothing but your the H there which we have to consider, because I'm not considering here H because H generally in heat transfer we takes for your convective heat transfer thing, but to avoid the confusion I have just taken here delta X only. So delta X can be calculated from here, XL minus X naught divided by number of the difference point in between. Fine. Now again, I changed the delta X by M. Actually, that is the choice is yours, because if you want to write your MATLAB code, so delta X the writing looks very odd. So either you can prefer it H, or you can prefer by M or the some other variable, because you need not to write delta everywhere. Correct?
Yes, sir.
Yes, sir.
So for that,
Yes, sir.
I just converted here I plus 1 to I plus 1 divided by M square equal to this not here. Now I can write this equation. I can expand this equation from I equal to 1 to I equal to N. Correct? So if I want to write for I equal to 1, so this will become me 2, this will become 1, this will become there. So this is your first equation, right?
Yes, sir.
Same way, can I
Yes, sir.
write it for I equal to 2? So if I write for I equal to 2 here, so this is your first means the equation. So this T naught is the nothing but your temperature at the boundary, which is your known to you. So the known part you are taken to your right hand side. That is the known term, right? These two are
Yes, sir.
unknown, because I don't know T1, I don't know that T2. So this is my unknown, the temperature which need to be calculated. Same way, can I write the previous equation for I equal to 2? So if I write at I equal to 2, I will get this equation. Now here everything is unknown to me. I don't know the T1, I don't know T2, I don't know the T3. Right?
Yes, sir.
So,
Yes, sir.
so all the 3 points are the unknown, so they would remain on the left hand side. The right hand side again is 0. Now I can write the same thing for I equal to 3. So if I write
Yes,
for
sir.
I equal to 3, I will get T2, T3, T4 again equal to 0. All of these are means the unknowns. I can write till all n number of different points. So if I write for nth point, so here you wrote for fourth point, let's say I equal to n minus 1, you got this one. Then I equal to n is last difference point. So if you write at last difference point, you are getting Tn plus 1, 2 by this plus this equal to 0, where Tn plus 1 is your last boundary. Okay, this practically is nothing but your TL, because you are calculating, you are considering and the n number of the difference point between the boundaries. Means if you will go here, so here the problem which you are the formulated just now, your this n is not here, practically n is till this particular point, therefore you are getting this point would become your n plus 1, which is your boundary. If you are calculating your condition is the last that, so your last equation should be for I equal to n minus 1, so that you will get the last term here. One is Tn only, correct?
Yes, sir.
Yes,
So
sir.
your last point is your boundary point. So make sure that whether you are considering n number of the points or n minus 1. If you are considering n number of points here, so your last point here is n. So this would become this will become Tn plus 1. If you are considering this n minus 1 is the last difference point, then this will become your Tn. So you should means take care your last point would be your boundary point only, correct?
Yes, sir.
Right. So once you did that part, so you will get this. So all these equation now you can arrange them into the matrix. You will have practically n by n matrix now, because you have now n number of variables, correct? N number of unknown temperatures. Is that fine?
Yes, sir.
Yes, sir.
First equation will have just two temperatures, rest temperature coefficient are 0. Here, if you want to put T3, T4, T5, T6, T4, T7, and Tn. So here, all of those coefficients are the 0. So your first equation would have only two terms. The second equation, you know the T1 term is there, T2 term is there, T3 is there, but T4 is not there. From 4 terms onward, every coefficient is the 0. So you have the second equation, 3 term. Third equation, again 3 term. Fourth, again 3, again 3, again 3. So from first equation would have only 2 term. See the last one. Last equation would have how many terms? Because Tn plus 1 is the boundary temperature, which will go to the right side. So this also have only 2 terms.
Yes, sir.
Correct. So if you write in terms of the matrix form here, so this would become your matrix. Your matrix is, this is your the equation number 1, equation number 2, equation number 3 and 4, and keep on doing this. I just wrote how n by n actually. So because here you have dash thing. So this would become your matrix A. These are your all unknown, that mean the temperature T matrix. This is your all your boundary conditions matrix, which is are the known to you. You know the T naught and you know the Tn plus 1, which is your the boundary at the last one. Correct? Correct or not?
Yes, sir.
Now
Yes, sir.
this is you have to think that how can I generate this type of the matrix, because this is just, you can say, first line if you will not consider for time being, and last line if you will not consider for time being, you have completely a tridiagonal. I mean the matrix, you have a set, you have a central diagonal which is minus 2 by m square term everywhere. You have one is off diagonal to the left side, one is to the right side. So you have those terms are fixed also, 1 by m square to you, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
So you need to think that how can I generate this particular type of matrix using the MATLAB? Because once I know here what I need to do, if I want to generate this boundary condition of matrix B1, I will just write in 2 lines here, because here you have B11 equal to minus T naught upon m square, and B n comma 1 is also equal to minus Tn plus 1 by m, right, means square. So it will generate your entire B matrix, because the rest of terms are the 0. So MATLAB would by default would set it equal to 0. Correct?
Yes, sir.
So only thing you need to think that how can I generate this matrix actually from think some command. How can you think about it? And this is practically, you can say, what we did in this particular class just now. This is just you can say your finite difference, central difference formulation of your second order boundary value problem. Okay.
Yes, sir.
Yes, sir.
Is it understood to everyone? I hope it doesn't have the much complication. It is the easiest part, I think so. So you think that how can you just generate this particular matrix? And now I am going to show you the problem actually. So I generated, so I don't want to show the my code actually. So I want you to think actually, because your thinking capabilities should also develop, right? So
Yes,
let's
sir.
say this equation you want to solve. This is not from heat transfer, so I will show you the heat transfer one actually. Let's say this is the heat transfer one. So here, yeah, you can take also this one, but this is in the cylinder one. Let's say for bar one, metal bar, which one I have considered. Let me give you the metal bar question. Spherical boundary conditions. This. There would be a problem here itself. This is the problem actually. So what you have here, this is consider, you can note down this actually the problem statement here, that consider a large plane wall of thickness L equal to 0.2 meter. Thermal conductivity is 1.2 watt per meter per degree Celsius. And surface area A equal to 15 meters square, which is perpendicular to direction of the heat transfer. The two sides of walls are maintained. A wall are maintained at constant temperature T0 equal to 120 degrees Celsius and TL equal to 50 degrees Celsius respectively. Because that because if you want to solve one dimensional, you can solve it analytically also, right? So if you will solve it means analytically, you will get this particular expression for temperature, correct?
Yes, sir.
Right. So that this is your analytical solution, and based on that you can also calculate the analytical heat transfer also, which you can calculate by Fourier's law of heat conduction, correct? So that you can calculate from here. You have to make your MATLAB code by using your finite difference formula, using your central difference formulation, which we have talked just now. Develop a code for that and just generate the solution for that, and try to compare the two actually, analytical solution and the numerical solution, which you will solve it using your central difference formulations. So your temperature boundary conditions are T0 120, TL 50, length is given to you, that is your total L 0.2. Area of heat transfer is given, K is given. So try to think that how can you write a program for that. You have to think actually. I have shown you the full program. This would be the matrix. If you can think that how can I the generate this easily, just think about it, and that would be your first part for this. Currently you are talking about only your one dimensional heat transfer only for temperature boundary conditions, right?
Yes, sir.
Will it be fine till here?
Yes, sir, we will try.
Okay, so try to think it and develop the MATLAB code for this, and then try to solve it. And in the next class, actually, we will do for this. This is for your temperature boundary condition. Same thing can be done for flux boundary condition, right? So flux boundary condition, you can also formulate at the same time, but I can give you some hint for that. So if you will, you have time or you have class now? Just a minute, I can give you some idea for flux also. If you will write for flux, can anyone tell me that what is the heat transfer flux? Minus K. Hello?
minus K dt by dx.
dt by dx equal to, let's say how much flux you want to maintain. K, let's say you want to maintain by convective heat transfer, or let's say some place sometime flux is given to you that value, or let's say you want to meet by putting a furnace at one of the, and the furnace is providing your means totally your some sort of flux. So furnace will provide, let's say if you are taking in terms of heat transfer or atmospheric heating, so you have a convective heat transfer, and that heat transfer is going inside your wall, right? So that is your T, you can say the surrounding जो भी होगा minus your, what is your here? Practically your T naught, if you are want to calculate to this side, right?
Yes, sir.
This is your left boundary condition, right? So if you want to calculate this, if you want to calculate this, your x equal to 0. So this would be your flux boundary condition, right? Correct?
Yes, sir.
So this is your flux boundary condition, your the left side. Now you can write your again your first derivative formula for this boundary. What would be that? First derivative using the second central the difference formula. क्या था वो? T
T of I plus 1 minus T of I minus 1.
T of I minus 1 divided by,
2h.
so
2h.
2h, you can say 2 delta
Yes,
something,
sir.
Yes, sir.
right? Now from here what will you get? इस इक्वेशन को इक्वेट करके you will get your expression for T naught, क्योंकि आपके फर्स्ट इक्वेशन में you are getting the expression of T naught, right? फर्स्ट में जो अभी हमने सॉल्व किया just now, right?
Yes, sir.
So you
Yes,
will
sir.
substitute this T naught at that particular place and arrange the equation number 1 only. Fine. Hello?
Yes, sir. Can you
Yes,
please repeat?
Kya? What?
Sir, can you repeat?
Yes, from here you will get your expression of your T naught, right? आपको एक T naught का expression यहाँ से मिलेगा, क्या मिलेगा? This पूरा का पूरा and this divided by H, right? Correct?
Yes, sir.
And
Yes, sir.
this would become, let's say, this side or this side. Will it become plus?
Yes, sir.
A plus बन जाएगा, I hope so, right?
Yes, sir.
Yes, sir.
Yes,
So this
sir.
would be your T naught, right? Now this
Yes.
T naught would be substituted at your this T naught here, जो आपके पास equation था that from here, right? First equation you have this one, right? This is what need your T1, T naught, right?
Yes, sir.
At I equal to 1, you have only thing which you need to solve it here is T naught, and T naught is coming from your flux boundary condition. From there, you will put the T naught and arrange this equation there. Okay?
Yes, sir.
Yes, sir.
So that is your first. Same thing need to be done for your last equation Tn plus 1. So you will again rewrite for your this plus equation for again for your at x equal to L.
Yes, sir.
So there also you know the flux boundary condition. By chance both the ends your flux boundary condition are given. So you will put the heat transfer coefficient at that particular point, the temperature of the surrounding at that particular point, and this would become now your Tn plus 1, right?
Yes, sir.
And you will write again this particular mean that derivative for at n plus 1. So you will get here Tn plus 1 and this is your Tn minus 1, right? And this would become your Tn. So you will get the equation from here of Tn plus 1, correct? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So you will put that again in the last equation, arrange that actually, fine?
Yes, sir.
So that would be or the solution change, so your temperature one would change now your flux boundary condition. Okay? So these two you will try and then we will talk tomorrow for that. Will that be fine?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. See you tomorrow. Think that how to write this particular code also.
Okay, sir.
Okay?
Okay, sir.
Okay then.